In this video, we're going to continue our understanding of exponential growth and decay, and we're going to introduce the standard exponential growth model. All right, so why don't you pause, copy this guy down, and then we'll talk through it. From a week or two ago, we tackled a problem like this example here. So we have a town, and at time 0 years, maybe that's 2000, maybe it's 2010, whatever. At time 0 years, the town has a population of 840 people. And then we know that every year the town is growing by 12% each year. And a few weeks ago, we developed a model, a function that describes the population. And if you recall, we put the 840 there for the time 0 population. And then we did 1 plus our percentage growth, which as a decimal is 0.12 for 12%. And we get that amount of growth each year for t years. Okay, so after 1 year, our 840 gets multiplied by 1.12 to represent 12% more than the last year. The year after that, it's another 12% more, and 12% more means 1 plus 0.12. Okay, so we had that exponential model for our population. Today, we're going to look to sort of standardize this model. So in general, any quantity that exhibits multiplicative or exponential growth or decay, so growing by a set percentage each year or diminishing, decaying by a set percentage every year, any substance or object that follows this behavior can be modeled by a function of this form. The amount after t units of time is equal to a sub 0 times e to the k times t power. Now, a sub 0 is going to represent the initial amount that we had. And in other words, a sub 0 is going to be the amount present at time 0. And we're going to call this the exponential growth and decay model. All right, so why don't you copy that down? What I'm going to try and do is I'm going to try and take this function we developed over here and convert it into this standard form a0 e to the kt, all right? Okay, so first off, we know a0 is equal to 840. It's the amount present at time 0, and we were told that was 840 people, just like we used 840 in our first attempt at modeling this, right? My goal is to find k in this function a of t equals my a0, which is 840, e to the k times t. Right? So that's going to be my goal. How do I get the value of k? Now, we got a nice little thingy here. I know that 840 times 1.12 to the t power models the population, and I would like 840 times e to the kt to model the population. Okay. Right, so I can cancel or divide both sides by 840, right? And on the left, then I'm left with 1.2 to the t. And on the right, k times t, I could split that up into a t power on the outside and e to the k on the inside, right? Because remember, if I have e to the k raised to the t, I multiply the powers back together as I have there. Right? Now, we know that exponential functions are one-to-one. So if this raised to the t is always equal to this raised to the t, it must be that the 1.12 equals the e to the k. Okay? Or another way of saying that, I could take the tth root of both sides to kill off the tth power. Right? Right, so I'm left with this, and I've got to get the value of k out of here. And it's up in the power, but I have a really handy object that destroys e to the x's, the natural log. So I'm going to take the natural log of both sides. All right, so I get the natural log of 1.12. And I know the natural log of e to the k, the natural log undoes what e to the x did, returning just the x, which in our case is k. Right? Now, I punched in natural log of 1.12 on the calculator, and I got that k was equal to 0.113 0.33. So I went out to 4 decimal places for accuracy, which is pretty standard for your K value. Go 4 decimals deep. So ultimately, the function I'm after is A of t is equal to 840 initial population e to the 0.1133 times t. So if I want the population 10 years from now, I plug in t equals 10 and crank this out in my calculator. Right. Let's finish the video by doing 2 examples. Right. So why don't you copy down this first example and I'll work through it and then we'll go through example 3. A population of bacteria starts with 10 bacteria cells, whatever, 10 bacteria, and it grows exponentially, right? So it's important to know that it grows exponentially, not linearly. After 3 hours, there are 50 bacteria. The question is, how many bacteria are present after 10 hours, right? So we want to know how many bacteria are there after 10 hours. So since it's exponential, we know the amount after t hours will be A0 times e to the kt. It's my exponential growth or decay function. And I know the initial population is 10 bacteria. So I can throw in a 10 times e to the kt. All right, now to answer the question, how many bacteria are present after 10 hours? I'd want to plug in t equals 10, all right? But until I know the value of k, that doesn't help me crank out an actual number. So I first need to figure out the value of k. So step 1, determine k. And to do this, I've been given another data point. I have been told when t equals 3, a of 3, the output, is equal to 50. So I'm going to use this data point to solve for k. All right, so I've got, in slow motion, I guess, a of 3 is equal to 10 times e to the k times 3. And I know a of 3 is 50. So 50 equals 10 times e to the k times 3. Let me just say it's 3k. Sounds better that way. I'd like to solve for k. The first thing I could do is I could isolate the exponential part, the e to the 3k, by dividing the 10 to the other side. So if I divide both sides by 10, I get a 5 equals e to the 3k. All right, and now I'm trying to get k, but it's trapped up in the power, but I know how to dissolve e to a power. I can take the natural log of both sides to kill off the e. So I'm going to take the natural log of 5 equals the natural log of e to the 3k. And I can use my calculator, natural log of 5, I get 1.609, so 1.6094 if I go to 4 decimal places. The natural log of e to the 3k, the ln dissolves the e and just the 3k survives. So I could solve for k by dividing by 3. So divide by 3, and I get a k value of 0.5365. Okay. All right. So my exponential model is a to the t equals 10 e to the 0.5365 for k times t. So I've got my full exponential model. So step 2, I can now plug in t equals 10 hours from now. All right, so a of 10 would equal 10 e to the 0.5365 times 10. So that would be 10 times e to the 5.365. And if I do e to the 5.365 times 10, I get 2,137.9. So let's just say about 2,138 bacteria. the number of bacteria should probably be a whole number. Okay, so maybe a biologist would say, well, you got to round down. We haven't had that next one, but whatever, close enough. All right, so a lot of our work was to figure out the value of K, all right? And we're going to see that process again in example 3. Okay, so why don't you pause, copy this example down, and then we'll start. All right, so we've got this amazing substance, Axtelium, and we know its half-life is 44 years. So what that means is if I start with, 50 grams of it and just let it sit on my desk for 44 years, after 44 years, there'll be only 25 grams of it left. The other half will have, radioactively decayed away, all right? So, and another 44 years, half of 25, and another 44 years, half of 25, et cetera, et cetera. All right, so we got a half-life. We just start with a sub 0 grams of it. I don't know what that is. And I'd first like to determine the exponential decay function for this guy. And then I'm wondering how long will it take until only 10% of the initial amount still is on my counter or on my desk. Okay. So let's start with A. I am looking for the amount after t years. We know the initial amount is this constant, which I don't know, but this constant a sub 0. And then I know there's a k and a t involved, right? Now I'm never going to get the value of a sub 0. It's just a sub 0. It's just a number, but I don't know it, but I'll just deal with it. I do need to get the value of k again, though. And I have a data point. I have this half-life. So after 44 years, I know I should have 1/2 of what I started with. That's how much I should have left sitting on my desk. And according to the exponential growth or decay function, after 44 years, if I plug in t equals 44, I should have a sub 0 e to the k times 44. Okay? So understanding what a half-life is gives me this output for the function. And the actual desired form of the function gives me this output for the function. And I'm going to set those two equal to each other to solve for k. All right, well, the first thing I could do is I could divide both sides by a0. So I'd have 1/2 equals e to the 44k. And I'm trying to get the value of k, but it's trapped up in the power of e. So I do my, hopefully by now, starting to be natural step of taking the natural log of both sides. So I'm going to take I'll go over here, I might need more space. I'm going to take the natural log of 1/2, and that's going to equal the natural log of the other side, e to the 44k. And the natural log of 1/2, ln 0.5 is minus 0.6931. ln dissolves the e, and I'm left with 44k. So to get the value of k, I take minus 0.6931, and I divide it by 44. And that gives me 44 minus 0.015, 8. All right. So I've got a k value, and negative is good because a negative k value means we are decaying. A positive k value means we are increasing or growing, okay? All right, so I've got my function. My answer to part A would be, my amount function is that initial amount A0, e to the k minus 0.0158 times t, right? So there's my function that tells me how much I have after t years. All right, well, let's look at part B. So part B says, how long will it be? So I'm trying to find t for when the amount after that many years is 10% of the initial. So 10% of the initial would be 0.1 times A0. I don't know if I like the parentheses. I don't think I like the parentheses. So 10% of the initial is 0.1 times A0. Right? So I know my output of the function is going to be 0.1 times A0, and I'm looking for my input t. All right, well, there's my function. I know the output is 0.1 A sub 0. And I know if I have a t, I would have plugged it into the right-hand side, minus 0.0158 times t. So now I'm trying to solve for t. And it's almost an identical computation to what I had up here when I was trying to solve for k. My one unknown is up in the power. So I'm going to go through the same steps. First, I'll divide both sides by a0. So that will give me 0.1 equals e to the minus 0.0158 t. I need to get at the power, so I'm going to destroy the e by taking a natural log of both sides. All right, so I'm going to calculate the natural log of 0.1, so ln 0.1. That gives me negative 2.3026 if I round to 4. And over here, ln and the e kill each other off, and I get minus 0.0158 times t. So then I'm going to divide the 0.0158 negative to the other side. So t would equal the negative 2.3026 divided by the negative 0.0158. So I divided that negative 0.0158 underneath the 2.3, and I get negative 0.0158 plus or minus some rounding errors, 145.7. This is for t, so this is years. And I can do just a quick follow my nose to see if I think it's accurate. So I'm just going to go by half-lives. So I start with A0. After 44 years, I'm down to 50% of A0. After another 44 years, so that's 88 years, I'm down to half of 50%, so that's 25%. So 88 years, 25%. Another 44 gets me to 132. So after 132 years, I'm at a half of 25%, so that's 12.5%. So after 132 years, I'm at 12.5%. And it looks like if I go another 13 years, I go from 12.5 down to 10. So that seems reasonable, all right? If I want another half-life from 132, I'd be at 176 years, and I'd be at half of 12.5%, which would be 6.25%. So 10% is occurring in between 3 and 4 half-lives from now, which seems to make sense.